Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. It is an immense pleasure to welcome you all to this technical forum entitled Composite Materials, Opportunities and Challenges. This is organized by the Material Science and Engineering Department at KFUPM and as well as co-organized by the Saudi Arabian Society for Composite Materials. Composite materials are produced when two or more of the classical materials, metals, ceramics, and polymers, are combined to attain certain properties that individual component cannot provide. It has been, it is, and it will be always, with the variety of combination, be of a special interest from research point of view in the academia, as well as toward more deployment in the industries. So huge opportunities are there, but it comes with its own challenges. Luckily, we have national and international speakers who are experts in the field of composite materials. Not only that, but they are from academia as well as from industries to enlighten us about this topic from their lenses. Before we start, at any instances, you can always type your questions in the Q&A, or you can send it to me directly, and I will be happy to facilitate it. Or if you want to spell it out and you are asking a question, just raise your hand. I will make sure that you can do that. Without further ado, I will give the floor first to Dr. Turki Baroud, who is the chairman of the Material Science and Engineering Department, to give his own opening remarks. Dr. Turki.
Okay, so you see my screen?
It is clear.
Okay, that's great. Okay, so assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, good afternoon, good evening, wherever you are. I would say hi, hello, hola, ni hao, konnichiwa, and we are very happy to have you with us today. And I hope that you will find something useful at the end of today's forum. You know, at the beginning, really, I would like to thank our amazing speakers and for their time and from also the way that they are trying to offer help and support in order to make this a successful event. I also would like to thank Dr. Atif al-Zahrani, who put this beautiful forum together. He's one of the amazing faculty in the Material Science and Engineering Department. Also would like to thank in the beginning the Saudi Arabian Society for Composite Materials, more specifically Professor Gilles, for being with us from the beginning of the establishment of the department. Mentioning Professor Gilles, I cannot forget Dr. Abdul Jabbar al-Suyud, is also an assistant professor in the Material Science and Engineering Department, who connected us with Professor Gilles. Okay, so this is one of the initiatives that we have in the Material Science and Engineering Department, where we would like to bring a topic, but then in order to have a holistic view, we're trying to bring people from academia, from industry, in order to have this mixed opinions. So at the end of the day, we try to cover a certain topic from different perspectives. I know I'm not going to talk about composite. I'm going to talk about material science, about the department. I was thinking, what will be the unique thing about the department that I would like to share? But before that, let's remember, we are not the only creature on this planet where we are able to, make something, right? There are other creatures sharing with us this planet where they can, build, right? They can make things, they can build a nest. The termite, they can build the tower, right? The beavers can build the dam, right? So it's not about the ability to make. What makes us special as a human being is the ability, is the competence that we have, and also most importantly, is the ability to expand and adapt that competence. And that is, clearly reflected if you look at the ages of mankind. From the beginning. You look at the not only different ages named with the materials that dominating that age, the Stone Age, Copper Age, Bronze Age, Iron Age, right? It's not only about that, but also the ability to make a certain material useful for certain application. Or in other words, having a problem, and then how can we let that material serve that application? And in case that materials cannot serve, let's find other materials. And how can we use the same material by playing with the properties, playing with the structure, whatever, in order to make it more and more useful. So I would like you to remember this as we are going forward, that what makes us different when it comes to material is the ability to expand and adapt that competence. And this is very, very important. You know, in order to do that, with the advance of technology and the complexity of the technology that we rely on today in our life, we have to see the holistic view when it comes to materials, right? We have natural resources, and those natural resources will let us to have a material that can be used for certain application. So it's very important to know what are different types of material exist, and then what is the problem that we have and then we want to use that material for that application. And then after we use that material for that application and the material is already in use, then what kind of issues that material can show, right? How the material will behave in that application, whether it came of failure or degradation, right? And then the question, a very important question, you know, what we will do at the end of the material's life, right? So then, because, you know, as you have a high competition when it comes to material, right? The nature cannot continue providing that kind of material. So can we recycle the material again and to feed the same industry or maybe new industry? Think about lead acid batteries and what's going to happen to it as electrical vehicle motors become something that we will be seeing every day in the road instead of other types of cars, right? So having this full picture and having people who see this full picture and be able not only to design, understand the property, the structure of materials, but also using it for certain application to address grand challenges, whether that it comes to water or energy or the environment that we are harming today by, you know, either through the carbon emission or through utilizing or through recycling or the waste that we are dumping into the land. So the many issues and materials always there to fix these issues. Now, because the problem is not in a small scale, right? And if you look at the value chain, right? The value chain. It's not about bringing material for certain a problem or certain technology, but about developing and providing talents to the job market, right? Who's able to continue that efforts of designing and providing and synthesizing materials that will help in different applications. This is why here at KFUPM we felt, it's very important. And before that, again, so different types of polymer, we see that there is a big demand for it, regardless what kind of plastic you're dealing with. Many applications in packaging, construction. And now if you look at the ceramics, the same thing, wide range of applications. The global demand is also increasing. The same thing, also the topic today, composite materials. You see there is an increase in the demand for composite material for different types of applications. This is why here at KFUPM, we say that it's very important that we go ahead and, and start something that's completely dedicated to material science and engineering. So in April 2021, KFUPM decided to establish the Material Science and Engineering Department. Now, this is not something unique, right? But what's unique about is, along with the graduate program that we have, we are for the first time, and this is actually the only program here in the region, providing and offering bachelor's degree in Material Science and Engineering. So it's very important that if there is a take-home message from my talk today is that we are here trying to provide to the future jobs and for the market, for the business needs of different industry, people who are very expert, they are ready to impact the journey when it comes to materials. Okay, so what we're expecting from our students here and what we're trying to do is we're trying to prepare students to be able to design, synthesize, process, and characterize different types of materials. I want to walk you very quickly here. This is the bachelor degree of our the bachelor program in material science and engineering. So now here excluding the first and second year, there's a third year sophomore where the students start their journey in material science and engineering. So the first year, the student know different type, he will be aware of different types of material, whether ceramics, metal, composite type of materials, and then thermodynamics, what encourages certain material to behave in a certain way, right? So he's going to learn more about Gibbs-free energy and other governing equation. And then, structure, very important, and defects. But the student will look at the defects, not an issue, but also an opportunity for wide range of applications. And then diffusion and kinetics, materials characterization. So the student will be aware, will be introduced to a wide range of characterizing materials, as XRD, SAM, UVVS, XPS, different way of characterizing the materials. Ending the first year, now we take the student, tell him, now we're going to give you dedicated course in each type of material, each main class of material, right? So here, in the first year, you know about different types of materials and their structure, how to characterize them. And now in the second year, he will learn about the property structure relationship for each class of main class of material. So there is a dedicated course for metallic material, polymeric material, ceramic material, and the topic of today, composite material. So we are not making this forum because we think forum is important, composite material is something good to consider, but we believe it is very important. This is why we have it as a core material that each material science and engineering students will not graduate before taking course in composite material. And also we have course in failure of materials and prevention. But knowledge is important, but what's also important is the hands-on experience. This is why, when you deal with materials, you can start from scratch. So this is why we have material synthesis lab. The students go up to the lab to synthesize a wide range of materials, nanomaterials, porous materials, and then also they have hands-on experience in materials processing lab, where they will do injection molding and different other types of materials processing. And also they try to see correlate between structure and processing property. And then in the final year, more into dedicated course, electronic optical properties and material selection. And then you see here 4 elective courses, and those 4 elective courses we want to give an edge to our students before they start their next chapter in their life, right? And this, as of now, we have 5 important areas: computational material design, metallurgy and mining. Anyway, mining is very important for the country. That's considered to be the 3rd pillar for the economy of Saudi Arabia. The other thing, materials for water and energy, corrosion, degradation, also non-metallic material. We believe that it's not about delivering. It's not only delivering courses will make a delta in the student experience. What actually makes the delta is how you can encourage them to see a problem, right, and then utilize their knowledge about materials, right, to solve that problem. And this is what we did with our undergraduate students. So we encourage them to see existing problems and to start research very early on. By the way, we told them no expectation from our side, and you shouldn't have expectation. It's only exposed, like you're exposing yourself to research and to different types of problem, and then see how can we tackle that kind of problem. And our students, you'll be amazed. Around 60% or 70% of our students, they already started doing research with researcher or faculty in a certain topic. For example, one of the topics that we have these 2 amazing students, Khalid and Osama, they are starting to do research and developing how can we enhance or how can we come up with a screen protector for glasses. So they get into the lab, they use advanced equipment, whether in terms of the synthesis or in terms of the characterization. And remember, they are still in the sophomore year, right? And they are getting into this. Just imagine the projection of this at the end of their journey. Along with that, also we believe that it's not only what we do in the class, what we do with the with the courses and research, but also their soft skills, right? Their social intelligence. So the students very passionate about improving that and enhancing the social intelligence. And you can see this. So here we have Usama is helping the prep year student who decided to get into material science and engineering, how to pass the first year and the second year with excellent grade. It seems that I took more than what you gave me in the beginning, Dr. Atif, but I'm about to finish very quickly. It doesn't mean the excitement that you have and they share with you about the undergraduate program that we're not excited about the graduate program. We are very excited about. Actually, indeed, we have around 21 graduate students working different topics in water treatment or desalination, energy conversion and storage, environment, CO2 capture and conversion, failure and degradation, competition and design, and working with amazing faculty in that field. What I would like to note is that the master program we have, along with the core courses, we have more elective courses that give more flexibility to our students to focus in an area that help them in their research. Now, I'm assuming we have people from the industry joining us today. Please, this is an open invitation from me and from the Material Science and Engineering Department. We are very keen to establish good partnership with the industry, and already we did. So with developing the degree plan, we had many meetings with individuals from SABIC and from Aramco and from other companies in order to develop the degree plan, in order to better prepare the talent for the business needs of the industries. So there are many ways and venues of collaborations, and today is one of them. I'm very happy to see it started. Okay, so I think I'm done, and my apology if I took more than what you gave me in the beginning, Dr. Atif. And thank you so much for this, and I hope this forum will be successful and everyone will find benefit out of it. Thank you so much.
Okay, thank you, Dr. Turki, for bringing up the Material Science and Engineering Department and how it can contribute to many topics, including the composite material. Now, I will leave the floor to Professor Gilles. I will introduce him in details when he's giving the technical presentation, but Dr. Gilles now is the chairman for the Saudi Arabian Society for Composite Material. Dr. Gilles, the floor is yours. You are muted, by the way, Professor Gilles. Professor Gilles, can you unmute yourself, please?
Okay. Can you hear me now properly?
Yes, I can hear. Yeah, perfect.
Okay. I'm coming to this. Okay, good. Thank you very much. Can you hear me properly now and everything?
Everything is perfect. Thank you.
Good. Thank you. So thank you so much for the invitation today. I mean, the first thing I want to express my gratitude to Professor Turki and to Professor Atif for the leadership on organizing this event. I mean, this is clearly a great thing when it comes to building new composite-oriented facilities and skills in KFUPM. So what I would like to present today, it's in a nutshell, in a few minutes, the Saudi Arabian Society for Composites Material that co-organized this event today. So I guess that some of you already are a member of this, and the others probably don't know about this. So let me give a few points about this. So the Saudi Arabian Society for Composites, that you will know as SASCOM, this is our short name, is a learned society that has basically four objectives. The first one is to exchange knowledge about all aspects of composite materials, and is about connecting scholars, professionals, and experts from all over the world. So this is really to create a network about composites that is going to be efficient for all the members. So we can share information, we can share networks, and we can grow together on this. The second point is about to promote both national and international collaborations. So development of projects between different entities, and then to develop and promote an educational offer. So there is a strong part about education, about training in composites. And the last one is about to support our partners when it comes to provide an expertise on composite materials for different projects. So who are the people who are behind SASCOM? So I think this is also important because the quality of a learned society is related to the quality of the people in the board. And from the beginning, when we built this society a little bit more than a year ago, excellence is really the guiding principle for this society. So as you can see in the board here, this is only one part of the member of the board. You have leaders from Saudi Arabia, from the kingdom, both from industry and from academia. And you have also international leaders from Europe, from UK, from the US, from different countries. So this is very important because this is going to connect you right away to a large network of people, including editors of journals or people who are running major composite centers worldwide. So I wanted to thank them today for being part of this board. So there are a few people who are more leading the day-to-day activities. So I wanted to especially highlight this 5% because they are the one who are meeting with me every meeting about technical meeting about SASCOM. So 3 of them are part of my team, the mechanics of composites for energy and mobility. So Mohamed Serraj, Arif Yudanto, and Wiping Shen. And then Professor Arifai from Yambu and Dr. Almu Hamadi from Aramco. I saw that Majid is here today on the call. Are also part of this team. So the society today, it's roughly 140 people. So it starts to be quite large actually for a composite society. And you can see that there is a share between academia and industry because we have pretty much 75% of the members from academia, 25% from industry. And what is good is that you have a representation from all levels, from PhD to master to bachelor degree to engineering degree. So this is really a broad network, but now has an impact worldwide because we are present in a little bit more than 15 countries. This is especially due to the wide impact of Saudi students when they are going for studies abroad. So they are getting connected to the society, so we can connect their local network with our network when they want to come back to the country and so on. So this starts to have a quite very international impact. And actually our objective is to link Saudi Arabia with the major academic societies when it comes to composites. So that means the European one, ESCM, the American one, the American Society for Composites, and also the Asian one, the Japan Society for Composite Material. So why joining SASCOM? So just in 1 minute, what are the different activities that we offer to our members? So we are trying to develop our activity along 3 lines. So the first thing, what we call SASCOM MasterClasses. The second one that we call SASCOM Experts, and the last one that we call SASCOM Events. So SASCOM MasterClasses, this is all about education and knowledge. So here's the point is really to provide to our members a unique series of master classes on composite technologies. So these are sometimes online or on-site classes that can be on generic or specialized topics about composites. These are very high-level classes or specific highlight, or they can be introduction classes to composites. They are all delivered by world-class researchers and engineers, people who are extremely active in the field, so you can also develop your network. And all our members receive at the end of each training an official certificate with a unique identification number. So just to give you an example, these are the 2 last classes that we run. So that means there was a 16 hours training by Professor Camano from Porto and Professor Altero on introduction to composites. Just 2 weeks ago, we did a training on composite delamination with Professor Daglia from ENS Paris. And we have more classes coming in the spring. So this is really, I think, a unique offering for students or engineers who want to get more to the point in specific aspect of composite technologies. Then the second thing that we provide is what we call SASCOM Experts. So this is more about expertise and technology support. So what is the objective of this? But at the end of the day, with this network, we have access to a bunch of people with very different backgrounds, going from polymer chemistry to composite mechanics engineering, experimental mechanics, computational mechanics, large composite structures. So what we can do is that we can always activate this network to address specific requests from our industrial partners. So sometimes people come to us with a specific expertise that they don't have locally, and we might have or not have this expertise, but at least we are able to connect to specific people. So if you have a request in this direction, you can, if you go to our website, you will see that there is a specific link for composite expertise where you can contact us, and we will try to do our best to connect our members with this network. And the last thing that I wanted to highlight is about what I call SASCOM Events. So the objective here is to create a network and igniting project by developing more interaction between members. So here we do three things. The first thing is a monthly seminar. So every month you have a very high caliber seminar on composite related topics. So this is the first Wednesday of each month. So for example, last week we had Professor Salah from King Abdulaziz University. And in the second week of March, we will get a talk from Professor Todoroki from the Tokyo Institute of Technology in Japan, who is a very well-known expert both on monitoring and 3D printing and composite integrity. So he's going to deliver a talk for our society. So what is important is that all our speakers are potentially people who have been plenary speakers or keynote speakers in most of the international conferences. And then we also provide some conferences. So we are planning to organize a Saudi Arabian conference on composite material. We organized the last semester, we organized a future composite workshop that was here at KAUST with 23 speakers from all over the world about composite engineering. In a few months, we are going to participate with Aramco to the MICCON 2022. That is an online conference about composite engineering. So this is mainly what we do. So in terms of how to find us and how to register, so finding us, you can go to our website, www.sascom.org, and you will see here that there is a registration tab there that you can follow. There is a membership that is free for the time being because we want to build the community. There is also an institutional membership that is available. In this case, you can directly contact us if you want to be associated with the society as an institution. And you can also follow us on Twitter at Saudi Composites, where we disseminate the main information about our classes and seminars that are coming. So I think this concludes my talk. So what I want to say is that this is mainly done to open many opportunities for collaboration in many different fields, going from large volume market, packaging, civil engineering, automotive, to dedicated composite solution for oil and gas, advanced application in aeronautics and aerospace, robotics, composite for renewable energy, composite for smart health. So we aim to have an impact in all these fields in terms of training and research. And really what we want to do is to federate a network of experts for training and collaboration in GCC and beyond. And to also to create something that is going to serve our members in terms of career development, job development, and network opportunity. So I think this is concluding my talk. So I hope that now you know more about the Saudi Arabian Society for Composite Materials, and you are all welcome to join if you want to continue this great adventure with all of us. Thank you, Professor Atif. I give you the floor.
Thank you, Professor Gilles. And I encourage all the attendees to participate. I know for sure that the material science and engineering students are all part of this and they like it. So I encourage all of you to participate in this SASCOM and register. So our next speaker, whom we are fortunate to work together to organize this event, is Professor Gilles. Professor Gilles is a professor of mechanical engineering and the Associate Dean of Faculty, PSE Division at KAUST. He's the director of the Composites and Heterogeneous Materials Analysis and Simulation and Integrated Environment for Composite Engineer that he created in 2009 when joining KAUST. Current research interests include integrity at short and long-term composite material, inverse problem for the identification of constitutive parameters, multi-scale coupling techniques, multifunctional materials and modeling, nano and multifunctional materials and devices. He collaborates with many industries from a variety of sectors, including energy sectors, the transportation sectors, or the consumer electronic centers. Before joining KAUST, Professor Gilles was a faculty member at the École Normale Supérieure University and a non-resident faculty member at the École Polytechnique in France. He also served as visiting researcher at the UC Berkeley following his aggregation in theoretical mechanics. Professor Gilles has a PhD degree in mechanical engineering and the HDR from the École Normale Supérieure University in Kachan. He has authored over 200 journals and conference papers. His work covers very wide expertise from material science to composite engineering and computational mechanics, as testified by the diversity of his publication in journals such as Advanced Materials, Journal of Mechanics of Physics Solid, Composite Structures, Nanoscale, Small, etc. He received the Daniel Valentin Award, recognizing his accomplishments in the science of composite material. He is also a board member of various journals, including the International Journal of Damage Mechanics. Professor Gilles recently is an elected member of the European Academy of Science and Arts. Let's welcome Professor Gilles, who will present a topic of improving the toughness in composites by design. Professor Gilles, the floor is yours.
Thank you very much, Professor Atif, for this nice introduction. So everything, the voice is clear and the slide is full screen, ready to go?
Yes, everything is perfect.
Thank you. So welcome again, everybody. This presentation is a little bit, you got very excellent, let's say, industry presentation. This one is more from the academic side to think about the next step and take it more as a class for young students about the way you can engineer microstructures to tune the properties and the performance of your composite structure. So what I will discuss today, it's about how can you improve the toughness in composites by design. So how can you tune your microstructure to increase the performance in terms of toughness and resistance to crack propagation. So this is a work, I just take 2 seconds to introduce the team behind this. So this is a work that has been developed in the labs for mechanics of composites for energy and mobility. That is actually my group at KAUST now. So this is a group that I'm very proud to work with. You see young people, extremely motivated people. What is very characteristic of the team is that we are working really in between experimental mechanics and computational mechanics. So that means if you join the team or if you are interested to work with the team, you have 50% really working in experimental, 50% in computational modeling and simulations. And this diversity of background is really much what characterizes the team, because actually, if you look, we are publishing in journals that are going from applied math, computational mechanics, high performance computing, also in journals that are more traditional composite engineering, like composite science and technology, composite structures, and so on, but also in journals that are more, let's say, new concept or material science oriented, like soft robotics or advanced materials. So that means we have a wide spectrum of activities. And I think this is really what defines the group in terms of uniqueness. That means the way, the ability to approach composite problems from very different angles and to look at really the multifunctional aspect and multidisciplinary of composites. So if I come to this specific work has mainly been done in collaboration with these 5 persons. So Arif Udanto, Rantao, Ahmed Waghi, Sheoleli, and Majed Hashem. So what I will present today is mainly the result of their effort in collaboration with me. And what is the objective? So the key objective is that you have, you know that today bonding between different materials, being able to bond metal to metal or metal to composites or composite to composite is something that becomes increasingly important in all industries, aeronautics, civil engineering, energy, wind turbine, solar energy, or even automotive. And if you want to assemble together different composite structures or different structures, the way you do it today is that you rely a lot on what you call conventional fastening technologies. That means you are going to use a lot of rivets and bolts. And of course, when you do this, you are facing limitation because this is introducing stress, concentration, weight increase, and it's not very good when it comes to long-term response. So what everybody wants to do now is to go to what you call integral adhesive bonding. That means we just have an adhesive bond line in between the part. And I have to say that this works very well until the day where it doesn't work at all anymore. So why? Because this is very difficult to inspect when you have an adhesive bond line like this. So inspection is a problem, integrity and monitoring, structural health monitoring is a problem. And I will come to it for the last slide of my presentation. But what is also a problem is that these joints, they all fail in a brittle manner. That means when you have a composite joint, it works very well until the day where you start to have a quark initiation and then an unstable quark propagation, and you completely lose the application, the integrity in a very short time. The performance of this kind of adhesive joint, it's very dependent on the pre-treatment of the surface, or mechanical treatment or chemical treatment. And the treatment that exists today on the market, they can be very different because they are very operator dependent, like the mechanical treatment, or they are very demanding in terms of chemical product, like the chemical treatment here with a large volume of chemical waste that will have to evolve because of health and safety regulations. So if you look at this joint, today the way you improve the integrity of composite joints, you have different techniques that exist in the literature. What you can do is that you can introduce corrugation in the substrate. So that means change in geometry between the two substrates to make sure that you will introduce mode mixity in the quark propagation. Or you can introduce something that is very, very classical, what you call Z-pin. So that means three Z-direction pins that are going to connect the different layers together. Or you can introduce what you call an interlock intersect fibers. So that means plies that are going to interlock together to provide some toughening during the delamination. So all these technologies, they exist today, but they all share what common problem is that at some point, they compromise the integrity of the substrate. That means whatever you are doing here, of course, you are going to toughen your joint, but you are going also to reduce the resistance and the integrity of your base composite substrate. That is absolutely not what you want to do when you work in composite engineering. This is true for all the techniques that you have on the market today. And we have, from our side, we have three challenges. First, we want to improve the intrinsic performance of adhesive joint. This is one thing. But more than the intrinsic property itself, what we want to improve is the mode of failure. We want to change from brittle to progressive. What is more important is to have time for inspection, to have time for maintenance, so to make sure that you don't get an unstable failure every time you have a delamination propagating in this. And we want to do this without compromising the substrate. That means we want to have a technology that is what we call an all-in-adhesive concept, and I will come back to this. That means we only modify the structure of the adhesive bond line, and based on this, we will change the response of the joint, and we will go to more safety in joint design. So I will present today quickly two concepts. One that is based on structuring. So if you have two substrates, so substrate 1 and substrate 2, and you have an adhesive bond line in between, the first technique that I will quickly introduce is by structuring the interface between the adhesive and the substrate. And the second technique is by structuring the adhesive bond line itself. That means the layer of resin that you are putting between the substrates. So I will just give an overview of these two techniques, that are two of many techniques that we develop in the lab. So if you want to get a tougher joint, what can you do? So the first path is by structuring the interface between your composite and the bond line, between the composite and the interface. So if you want to start to engineer the surface of adhesion between your adhesive bond line and the substrate, you need to have a technology to pattern to modify the surface of your composite in a way that can be very easily controlled. So the way we do this is that we do it by laser treatment. So just a very quick shot about this laser treatment. So you know that you are going to irradiate the surface with a certain frequency. And the efficiency of your laser treatment depends on what you call the fluence. That is pretty much the quantity of energy per unit surface area that you inject on your surface. And what is important to understand is that depending on the fluence that you are using, so this is typically a Teflon, a classical composite surface. This is when you are using peel ply, so you recognize the fabrics. This is when you are using sandblasting or sanding. When you are using laser, depending on the energy that you put of the fluence of your laser, you can get completely different treatment. You can either get a surface effect, but will only clean the chemistry on the surface, so just surface cleaning. Or you can have a more ablation effect. That means you will completely vaporize your resin, expose the fibers, so completely change the morphology. So what is important to understand is using laser, you can relatively easily control a pattern in terms of chemical properties of the surface, functionalization of the surface, and in terms of morphology of the surface, in terms of geometry of the surface. So you can really use your laser as a way to introduce patterns. So why introducing patterns is important? By introducing patterns, it's important because you can make a very simple numerical study at the beginning to understand what is the effect of heterogeneities on the propagation of quarks during a delamination. So let's start by a very, very, very simple example that you can all run here. So you take a DCB beam like this and assume that this DCB beam is made of two substrates, and then you have the adhesive bond line is the yellow layer here. And this bond line is connected by two green interfaces that are the interface between the bond line and the substrate. And you imagine that this one is heterogeneous. That means you can have some weak properties, so weak toughness, weak strength for the light gray, or you can have some strong properties, strong toughness, strong strength for the small inclusion here. And now you wonder what happens to a quark that is propagating through this interface in case that there are some heterogeneous properties like this. And what you will see is that you can face very different configuration depending on the relative value of the dark gray and the light gray. So the first situation is that your quark is going to propagate through the interface. I mean, without anything special, it will go through the weak area and then it will go through the strong area, and your quark will propagate. And this is a very classical DCB propagation. So you expect to see a load displacement curve that is like this one, a P delta curve. So for those who already did some DCB delamination, I mean, you recognize a classical DCB. The only thing that you can see is that when you go across the local reinforcement here with stronger properties, right, locally you have an improvement of the delamination curve, and you switch from the low toughness to the high toughness, but you don't get more than the performance of your superior surface treatment. Now, what is interesting is that when you start to play with the contrast, you start to introduce what you call bifurcation. That means that your quark is propagating at the bottom, and then at some point the quark gets pinned on the bottom here due to the contrast in properties, and you are going to initiate a secondary quark in the top. That means you are going to be able to initiate a ligament, and your adhesive bond line here will create a ligament between the bottom substrate and the top substrate. And instead of having a single quark propagation, in fact, you will have three quark propagation, one on the bottom here, one at the end here, and one on the back face on the top here. So of course, what is the immediate consequence of this is that you increase a lot the apparent toughness. Your P delta curve, instead of being here, your P delta curve is going to become very flat like this with a toughness that is going to increase when the quark is extending. That means your quark propagation is becoming progressive because you have this increasing R curve. So here you start to see the path towards engineering the microstructure and controlling the response to quark propagation of your interface. So of course, this mode of delamination depends on how much your ligament here is going to survive, and you have a third mode of failure. That is a situation where you start to initiate the ligament, you start to have a local reinforcement, a local increase of the toughness. This is the toughness as a function of the quark extension. So toughness is increasing, and then you break your ligament and you come back to the initial properties. So what you want to do to be able to design something like this is really to play between these three schemes of degradations and to be able to control this one. That means to be able to control the development of ligaments that are going to get a tougher joint to increase the property of your joint. And what you realize when you make simulation on this is that in fact you can completely predict this by numerical simulation. You have a design space that tells you that if I have a certain ratio in strength and a certain ratio in toughness between these two domains, I have a certain window here for design when I can control for sure that I'm going to create ligaments that are going to introduce this toughening effect. So this is something that you can verify experimentally. So here now you are taking two composite plates, you make a kind of pattern laser treatment like this. That is, so you recognize here the different pattern that I was showing before with alternative properties of strong and weak, strong and weak, strong and weak. And what you see during the delamination now is something like this. Instead of a very simple macro quark of DCB delamination, you start to see the creation of a family of ligament bridging like this. And this is something that you control by design. And if you look at this is really beautiful because if you look at this, you have plenty of dissipative event of your bond line just by modifying the surface treatment that you put on your composite before. And this is something that in terms of properties, if you look at the effective properties now, your P delta curve now is going to look something like this. And you can see that the toughness, the one that you measure from a macroscopic point of view, is multiplied by 3 or 4. That means you increase by 300, 400% the performance of your structure without changing your material. You just change the way you architecture the material. And you have really huge improvement to get from such technology. You see here the increase of the R curve between the baseline, that means what you will get without any patterning, to what you get when you are designing this pattern. So this is the first thing that I wanted to share with you. It's something that has been demonstrated in mode 1. It has been demonstrated in mode 2. You can see on a small structure like this, like a T-joint reinforcement, you can see that if you make a surface treatment like this at the interface, you are going to create something ligaments during the failure of these T-joints that are usually stiffeners that are used for composite structures. And based on this, you will see that this is the load extension curve. That means the force displacement curve that you get from the pristine structure. If you start to introduce this kind of treatment, I mean, you don't modify the composite, anything, you directly go to an improvement that is by a factor of 3 to 4. So this is really huge in terms of improvement. There is a second technique that we developed that is now structuring the adhesive itself. So structuring the adhesive for us, it's based on now making sure that the adhesive layers that is going to break is going to dissipate as much energy as possible during the delamination. And this we do it by introducing an hybrid adhesive bond line between the substrate. So that means we introduce thermoset and thermoplastic composites together. And if you engineer this completely correctly, what you get in terms of delamination is something that looks like this. That means if you engineer this properly, you give enough freedom to the thermoplastic to stretch and to expand and to dissipate energy during the delamination. And this is something that here again, when you see this is going to give a huge improvement in your curve, because this is in orange here, you have the original curve without thermoplastic carrier. And in blue here, you have the modified curve in which you modify in a correct way with thermoplastic inclusion, and you can greatly increase the performance of your system. So I don't want to insist too much on these things because I mean we could discuss this for a long time, but I want to keep time. So I still have 4 minutes, so I will go to the conclusion for this. What I wanted to show you here, what I wanted you to be convinced is that you can manipulate the performance of your composites the way you want. And especially you can manipulate the R curve just by modifying the microstructure in a better way. So here I showed you 2 paths. The first one is the introduction of heterogeneities on the adhesive substrate interface. The second one is the introduction of additive heterogeneities in the adhesive bond line. There is a third approach that we are testing now that is actually the more, let's say, biomimetics approach in which we are introducing sacrificial quarks in the interface. So this is inspired more from biological adhesion system, in which when you look at the adhesive bond line of very adhesive system, you have a lot of micro voids in this system that are here to promote the dissipation of energy, and by then to increase the effective toughness of this system. And this is something that we do in the lab by introducing sacrificial quarks in the adhesive bond line. And here again, you have an additional step of performance that is coming, because you can create multiple fragmentation inside the adhesive bond line by doing these kind of things. And this is a third promising path. What is important in this is that all the technology that I have shown today, so 1, 2, and 3, they are all compatible with what I call an all-in adhesive concept. That means we don't touch a substrate. Everything is coming in an engineered tape with different modification in terms of thermoplastic inclusion, patterning of the interface, in terms of introduction of sacrificial quarks. So what we are doing now is that we are creating this product, but integrate together these three points of understanding to make sure that we can deliver super high performance tape for adhesive bonding of adhesive joint. So this is what we are closing now. What is the next step for us? Now the next step for us in the team is really to work and to solve the bottleneck of, I was saying at the beginning, of monitoring of these structures. You know, structural health monitoring is always a nightmare for composite structures, and nobody knows really how to do this today. There are a bunch of techniques available on the market, but most of them cannot be used either in situ or real time. So what we develop in the lab is a completely disruptive technology that is going to make now these joints and these composite structures multifunctional, so they can be interrogated in a wireless manner. So we have here new technologies that is based on inductive sensing, but what we patented already, and that we are expanding to different type of composites. And this is really for us a challenge, that is making sure that composites are going to be tomorrow multifunctional enough to be interrogated in a wireless fashion, so you can control them in an easy way for easy composite integration. So this is a couple of papers that we did around this topic. If you are interested to follow up on this work, you are, of course, you are very welcome to write me an email. So gilles.lubineau@kaust.edu.sa. This is a web page for the group here, or the Twitter for our group. And then, of course, here again, I insist about the Saudi Arabian Society for Composite Materials. All the activities that we are doing here, we plan to promote them and to develop collaborations, and we are very open about collaboration on these topics, either through direct collaboration with the team or with collaboration through SASCOM. This is really the point. So I think this is concluding my talk. I am exactly at 20 minutes. So Professor Atif, I give you back the floor.
Thank you very much, Professor Gilles. Sure. First of all, I would like to thank all of you speakers, panelists, for accepting the invitation, enriching this technical forum. I would like to thank also the audience. We had a very good number of audience. I mean, more than for sure the average number of technical forums audience, for their questions, for their participations, for asking the questions, the right questions. This is something amazing, I mean. And what I can see, which is basically what I was aspiring out of this technical forum, is to plant a seed when it comes to moving this field, composite material, and general material science forward, especially as us, a young department within the kingdom and within the region when it comes to material science. So I'm hoping this is not basically the end of the forum, but actually it's the beginning of a real journey to enable the composite material within Saudi Arabia. This is really what I'm hoping for, and I'm pretty sure that we will be talking a lot later on. So with that, really, there's no word, no thousands of words to thank you, gentlemen, for your time and your talks. I conclude from my side. Dr. Turki, if you want to add something or if any final thoughts from you, gentlemen, that would be great as well.
Dr. Atif, thank you so much for such for organizing such wonderful forum. I think I would like also to thank all the speakers. It was really an amazing forum, especially getting to know amazing people and hearing from them. Very rich information. And by the way, this is a recorded forum. So the benefit of this will not stop here, but also it will be conveyed to more other people and students. And before we end, if Dr. Atif, I think there is a flight you would like to catch. So thank you so much. You can leave. Thank you so much for all what you did. If the speakers allow me very quickly, if you can stop sharing this slide. Okay. Okay. Great. So if I can just take 30 seconds from the speakers, or 20 seconds, or let's say 30 seconds. What is your message to our students who decided to major in material science and engineering? They're very passionate about materials. 30 seconds, a brief message, and also final thought on this. But let's start with the message to them, because we see, I think all of them maybe with us today, and I think they are still in the early of their program, and I think would love to hear something from you. Let's start with maybe who would like to start? Professor Gilles, please go ahead.
Yeah, okay, I will take the lead. So for me, if I can advise them, is to be, I would advise them to be quite broad on the background. That means if you look at the way materials are evolving, it's all about multiphysics. Nobody is going to work only on polymers, on metals, on mechanics, on electronics tomorrow. I mean, so I myself, I will dream to have at least 3 or 4 degrees in different fields to be able to work more at the interface. And I think if they can work more on this, this is really something that is going to give them a unique profile and give them unique opportunity in the future. I think this is really important for them. That's my word.
Awesome.
Yeah, maybe I'll pick up from where Gilles left, because again, he said it very well. I would say, if I look at myself, I'm a mechanical engineer by undergraduate training, and then I spent my remaining 2 degrees in material science. And I think if I reflect back, I think the ability to really spend time across disciplines, chemistry, chemical engineering, mechanics, really makes you a much more well-grounded person, whether you decide to spend the rest of your career in academia or industry particularly. To be able to connect with all these people is very, very vital. That defines success in the future beyond just the educational aspects that you will learn in university. And I think I often think about it that we all are saying the same thing, but we have different languages. You know, a chemist will say the same thing in some way, a mechanics person will say the same thing in another way. And sometimes we get into a communication problem at the interface because we don't understand each other, and it gets to be a bit frustrating, I would say, yeah. But when you come to industry, you're going to be in the middle of all of these people. And magic happens when all of these people come together to make something happen at the end. So early on, when you're young, to expose yourself and talk all these languages, understand what people are saying, is very, very important. And I think that will hold you in good stead. And material science is uniquely positioned in the middle, you know, to bridge the gap. So that's all I would say, be multidisciplinary.
Okay, great, wonderful. Let's go to Dr. Jalal.
So what I can say, any specialty you will choose or whatever, material science is, you will never get bored. I mean, as soon as you keep curious and you try to find the self-motivation, you will enjoy your career. And as you have seen during this forum, there are so many challenges for you. So just be curious and try to find the self-motivation, and you will enjoy a lot.
Okay, great, wonderful, wonderful. Let's go to Engineer Abdulaziz. Engineer Abdulaziz, maybe, okay, so let's go to Mr. Barrett. Mr. Barrett, sorry.
Yeah. Well, maybe good to mention, my original background is metals processing and simulation, and I think some 12 years ago I made the move to become assistant professor in a group on thermoplastic composites. And the trigger for me was that I found, hey, it's a very diverse new area back then, but also something which is promising. Back then it was very promising, and it is still very promising. And I think there is even more opportunities than back then. If we take a look at new applications, solar, for instance, EV platforms, etc. So I think there is a lot to do there. It is a very challenging field still. It's very diverse, so multidisciplinary. And I can only give the advice, and that refers also to what has been mentioned previously, that make your own samples, go to the lab once in a while, try to understand its material, try to get the feel of it. And that's how I started as well. And that made it very, very appealing to me that, hey, there is so many things and topics about composites that we can still work there for 100 years probably. So a lot of things to do and a very nice, challenging things to do.
Great, great, wonderful. I think we covered all the speakers, right? Hopefully I did not forget anyone. So that was great. So would like to end here by thanking all the speakers, amazing speakers, and also our audience for the interactive and their questions. This is not the end of what we have with Saudi Arabian Society of Composite. This is not the end of what we can do. Wish you the best. At the end, this is Turki Baroud, Chairman of Material Science and Engineering Department, KFUPM. I wish you the best night, inshallah, and good night. Bye.
Thank you. Thank you very much.
Thank you very
Thanks
much.
for-
Thank you.
Bye.
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 Bye-bye.